Hello, welcome back to our online tutorial. We are still looking at probability, more especially on the probability basic rules. So far we've looked at a number of probability rules, starting from the additional principle, the multiplication rule. We went further from the multiplication rule. We talked about the aspect where events are independent, and we slot in into the aspect where events are dependent. So from the concept of where events are independent, that's how we derived the concept of conditional probability. And from conditional probability now, we're looking at another kind of rule when it comes to events, which is called the partitioned event rule. I'm sure a number of us should understand the meaning of partitioned, especially those who works with more of laptops. I'm sure understand when it comes to maybe partitioning of a hard drive. I'm sure you're able to relate what partition mean. So basically, if maybe the hard drive is 250 GBs, there are concepts whereby you're supposed to be able to partition that hard drive. You're able to divide the whole hard drive, which is 250 GB, into some partitions, into some parts, whereby as you are using the hard drive, you'll be able to sort of, you can save my data maybe in that part and that part and that part. So I'm sure maybe the whole 250 GB has been partitioned maybe per video or per tato, where you have local disk C, local disk D, and sometimes you have the local disk F. So it can be 3 parts, 2 parts, depending on how you've partitioned it. So I wanted to use the same knowledge under partitioning, relating it to this event. So I think talking about when it comes to the partitioned event rule, we're just looking at concepts where we are being told that, or maybe we're just talking about how this rule applies, is when in a situation when A can happen through multiple mutually exclusive pathways. So we're simply saying that the partition event rule is applicable, or maybe applies, the rule applies when the event A can happen through multiple mutually exclusive pathways. So where the event A can happen through multiple mutually exclusive pathways. What do I mean? For example, if maybe let's say B1, B2, B3 up to somewhere maybe Bn form a partition of the sample space. So now I'm sure we understand when we talk about sample spaces at this time around. Sample space is the total outcome of the probability, the total possible outcomes in this case. So those total possible outcomes form up what is known as a sample space. So if we're talking about B1, B2, Bn up to Bn, these partitions are more like partitions which form up a sample space. So the whole total sample space has been divided into these partitions. So maybe if the total sample space, if we're looking at the hard drive, so if we're talking about the hard drive, if this hard drive is 250 GB, this 250 GB has been divided into some of the partitions. You can call B1, B2, B3, Bn until I don't know. So now, what are we simply saying here? I'm simply saying that the partitioned event rule applies when the event A can happen through multiple mutually exclusive pathways. through multiple. What mutually exclusive means that these events these events are not happening at the same time. They are not mutually exclusive, meaning that they cannot happen at the same time in those cases. So now, if event A can happen through multiple, what are the multiples are we talking about? We're talking about these pathways. B1, B2, B3, B up to Bn can be more like partition of the sample spaces. So if event A can happen through these partitions, event A is happening through the partitions which you've made from the sample space. Now, we have to understand that these partitions which we're talking about are mutually exclusive, and their union covers all possibilities. So these partitions here, so we're talking about these partitions are mutually exclusive. By mutually exclusive, it means that they are not happening at the same time. So they are mutually exclusive, and we're talking about their union, and their union covers all possibilities. That's what we mean. So event A is happening through these partitions. That's the concept we're supposed to be able to understand there. So event A should be able to happen through those possibilities, through those partitions. Now, I want you to understand, if we have a sample in this format, let's say maybe if this is my sample space S, this sample space S has been partitioned, maybe let me say it has been divided pangati patatu. I can call this first partition to be B1, I can call this second partition to be B2, I can call this second partition to be B3. So if this is the case, now we are looking at an event A in the sample space. So this event A, maybe I can draw my event A as something like that. This is my A. So now, for me to get event A, the probability that event A can happen, there can be a possibility that event A happened that it is in a B1. Maybe, for example, if I talk about this part, the probability of me getting this part, I'm talking about the probability of getting event A given that it happened from B1. Or there's a possibility that it can happen from this part. Or there's a possibility that this event A can happen from this part. So this is where the partitioned event through is coming about, where we're simply saying that if you look at this whole A, the whole A is basically being formed by what? In short, the whole set A, this whole set A is basically being formed from A intersection B1 union A intersection B2 union A intersection B3. This is according to what is being shown to us in this nature like this. This whole Venn diagram, or maybe this whole rectangle box, is representing the sample space, but this sample space has been divided into some partitions. Partition 1, which we are calling B1, partition 2, which we are calling to be B2, and partition 3, which we are calling to be B3. But in this sample space, there is an event happening, which is the event A. So the event A here can happen in case where it is in B1, it can happen in B2, or it can happen in B3. That is why we are simply saying that the whole A here is made up of A intersection B1, which is this part, union A intersection B2, which is this part, union A intersection B3, which is this part. So now, when it comes to probability, we're now looking at it to say, oh, if what is going to happen now, if I'm talking about the probability of me having the probability of A, this is just basically the probability of A intersection B1 union probability of A intersection B2 union probability of A intersection B3. We are okay? Now, what is happening here, we have to understand that B1 B2, B3 until I don't know. In this case, I'm just using an example whereby it has 3 partitions, but in the definition, we're simply giving an illustration to say these A is happening through multiple mutually exclusive paths of B1 up to Bn. But in this case, the last partition is B3. No wonder I'm ending up to there. But if I was to consider up to Bn, it is union up to A intersection Bn. I'm sure we're able to relate to that. So now, this is what is happening here. So now, we have to understand that when it comes to this probability, we have to put into consideration how do we find this intersection. This is where we have to recall the previous rules. The intersection is coming from what kind of principle? The multiplication principle. But with the concept that these are mutually exclusive events. What is happening there? These are mutually exclusive events. This means that the probability of A intersecting with B should be equal to probability of A given B multiplied by probability of B. We are okay? So now, if I want to find A intersection B, probability of A intersection B, obvious probability of A multiplied by probability of B, the multiplication principle. But in this case, for me to find A, obvious there must be a certain A can be found in a certain partition. Can it be in B1, can it be in B2, or can it be in B3? So that is why I'm simply saying that probability of A intersection B, this is the multiplication principle. I simply say probability of A multiplied by probability of B. I'm sure you can relate the multiplication principle. But in this case, the probability of A is not just an exact probability of A. This probability of A can be found in a situation whereby it is in B1, B2, or at B3. That is why for me to find probability of A, it is given that it is in which partition. In which partition does A belong, as I am looking for this probability of A. So probability of A intersection B is equal to probability of A given that it is in B multiplied by probability of B. So this is where the total probability is coming about. So it means that if the probability of A is equal to probability of A intersection B1 union probability of A intersection B2 union A intersection B3, this is now giving me a situation where I can simply say that probability of A is equal to probability of A given B1 multiplied by probability of B1. Where is this coming about? This is coming from this first case. Probability of A intersection B1 is probability of A multiplied by probability of B1. But A is found in which partition? B1. Union is bringing in the concept of what? Addition rule. So if there is a union, automatically I'm simply supposed to sum up. Sum up the second part. Probability of A intersection B2 means probability of A given that it is in the second partition multiplied by probability of B2. We're okay? Plus, because this is a union, plus probability of A given that it is in the third partition multiplied by probability of B3. Now, because of this definition, I'm simply saying that B can more like be a partition, multiple partitions for the sample space. This can continue adding up until I reach what? Bn. So the total probability, let's say probability of A can still continue being added up plus plus up to probability of A given Bn multiplied by probability of Bn. So what are we simply saying? If A can happen through multiple mutually exclusive pathways, what are these mutually exclusive pathways? It can be B1, B2, B3 up to Bn. So the whole sample space has been divided into B1, B2, B3, B4, B5 up to Bn. So then the probability of me having this A is just basically probability of A given that it is in B1 multiplied by probability B1 plus probability of A given that it is B2 multiplied by B2 up to until I reach probability of A given that it is in Bn multiplied by Bn. So this summation gives me what is known as the total probability. So this event rule is also called the total probability rule. The total probability rule. So with that information, I'm able to find the total probability rule using the partitioned event rule. Now, let's look at a certain example there involving the partitioned event rule. We are being told that a bag A has the following items. So bag A, we're in short, we have 3 bags here. We are being told that bag A has 2 red balls and 5 green balls. Bag B has 3 red balls and 2 green balls. And bag C has 1 red ball and 4 green balls. So this is the information we have. Now, we are being told that if a ball is randomly selected, what is the probability that the ball is red? If the ball is selected, what is the probability that the ball is red? So we start. Now, we have to understand that in this case, if I was to pick the probability of red, it would be very much difficult because I'm looking at probability of red in the second place, in the second bag B or bag C. So now this principle is now going to be brought into the issue of total probability rule, of which the total probability rule is also called the partitioned event rule, where the bag, in short, the total sample space has been divided into 3 parts: bag A, bag B, and bag C. So in short, if I'm talking about the total sample space, it has been divided pangati patatu. There is bag A, bag B, and bag C. So if this is an event of red, then there's a possibility that I can pick a red which is in A or in B or in what? Or in C. Okay? So how do I find the probability of red? Probability that it is red is going to be given that probability red given that it is in A multiplied by probability of what? Of A. This is the probability of red R intersection A, this in this part. That's the probability of this. But we want all the possible outcome of picking a red. No one is called to total probability because we're going to sum up. The first probability considering A, the other one I'm going to consider that this is coming from, given that it is coming from B multiplied by B, plus probability of red given that it is coming from C multiplied by probability of C. We are okay? So now, that is the total probability for red. So now, what is the probability that it is red given that it is in A? What is the probability that it is red given that it is in what? In A. So, I'm going to say probability of red is equal to red given that it is A. So red given that it is in A, how many reds do I have in A? I have basically 2 out of how many balls? I have 5 plus 2, which is a 7. We are okay? Multiply by the probability of A. What is the probability that it is in A? A in this case has what? A in this case has total balls to be what? 7. out of which total balls. Yeah, so 2 over 7 multiplied by probability of A. Probability of A is what? 5 plus 2, which is 7 over the total number of balls, which is what? 7 in the first bag. This is 5 in the second bag, which is 7 plus 5, that's a 12. 12 plus 5, am I correct? 12 plus 5, that's 17. I'm going to have 17 there, like that. So, probability of A, R given A, is 2 over 7. Probability of A is 7 over 17. This outcome plus probability of R given it is in B, R given that it is in B will be, how many reds do I have in B? It's 3 over how many balls do I have? 3 plus 2, which is a 5. Multiplied by probability of B. Probability of B, I have total 5 balls multiplied by total 17 balls. Plus, for bag C, red given that it is in C, I have how many reds? 1 out of how many balls are in the bag, and in the C bag we have the total of 5 balls multiplied by probability of C, which is 5 over the total number of 17. So the total probability of red will be equal to this, and that can go, which is 2 over 17 plus this and this will go, which is 3 over 17 plus this and this will go, which is 5 over, sorry, not 5, but 1 over 17. So what is the total probability? This is the same common denominator, which is 17. 2 plus 3 plus 1, which is going to be equal to, this is 5, 5 plus 1, 6. So the total probability for picking a red will just be basically be 6 over 17 as our total probability for red. Using which kind of rule? The partitioned event rule. Now, we have example 2 here given to us, where we're being told that suppose a factory produces 60% of its product from machine 1. So we have 2 machines there. Factory can produce 60% of its products from machine 1 and 40% from machine 2. Then the probability of a defective item from machine 1 is 5%. The probability that a product is defective from machine 1 is 5%. And the product should be defective from machine 2 is 8%. What is the probability that a randomly chosen product is defective? So when you pick a defective product at random, what will be the probability that that product is defective? Given the probability that from machine 1 it can be defective, it's 5%, but from machine 2 it can be defective, it is 8%. So now, how do we find this? We are using the total probability rule, which is also called the partitioned event rule. So, using the total probability rule, what do we know under total probability? If we are talking about the probability that an item is defective according to this information, it means that we are talking about the probability that an item is defective given that it is from machine 1 multiplied by probability of machine 1 plus probability that an item is defective given from machine 2 multiplied by probability of machine 2. And these are the the total possible outcomes we're talking about. We only have 2 machines, machine 1 and machine 2. If we had machine 3, it means it could have continued. This means that we're talking about the partitioning of what? M is the one which is partitioning the what? the sample space. M is the one partitioning the sample space. So from M, that's where we are finding our defective item. Is it from machine 1, machine 2, machine 3 or so? But in this case, we only have from machine 1 up to machine 2. So the probability of an item being defective, it is probability of D given that it is M1 multiplied by probability of M1 plus probability of D given it is M2 multiplied by M2. Just replace now the values. What is the probability of D given that it is M1? The probability of a defective item from machine 1 is 5%. So 5%, this is basically the probability is 0.05. The answer multiplied by probability of M1. What is the probability of M1? M1, its probability is 60%, which is 0.6. 0.6. So this multiplied by that, the answer plus probability that a defective machine is coming from M2 is 8%. So this is basically 0.08 multiplied by probability of machine 2. Machine 2 is the probability is what? Probability of machine 2, the product is made from machine 2 is 40%, which is 0.4, like that. So once we do the mathematics and everything, we are going to end up with this times that, that's about that, blah 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 blah. That's 0.3 plus, yeah, 0.3. No, this is 0.03. Yeah, you can confirm with your calculators. 0.08 multiplied by 0.4, this should be 0.0848 times 4, that's 32, 0.032. So that by the end of the night, the summation of these two will lead us to 0.062 as the probability that this product is defective. So this is how basically we'll be able to handle this question using total probability. Now let's look at the concept of Bayes' theorem, Bayes' theorem, depending with where you come from and your dental formula, how you pronounce that one. So now, how do we handle the Bayes' theorem? So now, with this theorem, we have to have an understanding of the conditional probability rules. Remember the conditional probability rule? So, in this case, we're just simply saying that the Bayes' theorem is just helping us to reverse the conditional probability. So it's just helping us to find just to reverse the conditional probability. What are we talking about? I.e., we're just talking about finding the probability of B given A when we know probability of A given B. So just reversing it, are we able to reverse such cases? So now, what do we know under conditional probabilities? What do we know under conditional probabilities? What do we know? So we know that, this marker, we know that probability of A given B is basically probability of A intersection B over probability of B. That's what we know. So the same is happening if I want to find the probability of B given A. This is just basically a probability of A